Hello, dear students. Welcome to our channel OnlyPhysics JEE Grad. And today we'll be discussing JEE Advanced PYQs, JEE Advanced PYQs from the chapter Current Electricity. This will be the second video on this chapter, and the topics we'll be covering are cells Kirchhoff's law. So there are total 30 questions, and 15 we'll be discussing in this video. So let us start with our first question. Right. So we have a circuit is connected as shown in figure with switch S is open. When the switch S is closed, the total amount of charge that flows from Y to X. Okay, so look, how do we find that how much charge has flown? So initially we'll find what are the charges on these, and finally after the switch is closed, we'll find the charges on them again. And by computing these charges, we can calculate the amount of charge flown from Y to X or X to Y, right? So let's start. When the switch S was open, so this wire does not have any purpose here. So we'll just write it like this. So we'll just draw like this, okay? So these capacitors and these resistors are in parallel. So we have 9-volt battery, right? And this will be 3 microfarad and this is 6 microfarad. So the 9 volt is dropped across them and they will have same charge. So I'll write it as Q1 minus Q1 and this will be Q2 minus Q2. Okay, and we know Q1 and Q2 will be equal. So we'll just write it as Q1 will be equals to Q2. Now let's find the C equivalent for this. So C equivalent will be 3 into 6 upon 3 plus 6, which is 9. So it will be 2 microfarad. Okay, so now we can find charge Q1, which is equals to Q2, will be C equivalent C into V. So C equivalent is 2 microfarad and volt is 9. So we'll have 20 microcoulomb. Q1 or Q2, you can write any. Okay, now the situation becomes this. So we'll have this wire is connected. Now look, this whole part and this whole part is in series, right? So you can draw like this. So this is our capacitor and this is our first resistance. And now because if these are connected, like X and Y will have same potential, right? Are you getting me? So I've just connected it through a point. This is our second capacitor and this is our second resistance. Okay, are you getting me? So this will be our situation. Now look, these two are in parallel, these two are in parallel, and this battery is of 9 volt. Now the resistance, so voltage across this, let's say it is V1 and let's say it is V2. Okay. Now when the switches is closed after a long time, what will happen? The current through these will be zero. So the only way current can flow is in this path. Yes, are you getting? So this is I, this is I, this is I, right? Why I'm doing this? Because I want to find the potential drop across these. So yes, so this is 3 ohm and this is 6 ohm. So let's find the potential across a 3 ohm. So V1 will be, as we know, V is directly proportional to resistance, correct? So we can write it as 3 upon 3 plus 6, which is 9 into 9. So this will be V1. So V1 will be 3 volt. And V2 will be 6 upon 9 into 9. So it will be 6 volt. Yes. So V1, if V1 is a 3, then let's call the charge on this first capacitor as Q1 dash. So Q1 dash will be how much? So it will be C into V. So it will be 9 microcoulomb. And Q2 dash will be, so this is 6 into 6, which is 36 microcoulomb. Okay. Now are you getting me? So look, here the charge was 18 coulomb. So you can write it as the charge over here minus 18 Now, and here it was plus 18. This is minus 18. This is plus 18. And now it becomes, this is 9. This is minus 9. And this become 36. And this become minus 36. Yes. So what will be happening? Like it needs plus 9 coulomb so that it will become minus 9. And it needs plus 18 coulomb, right? And the total charge will must come from this y2x wire, right? So y2x provides how much? 18 plus 9. So 18, yes, so 18 plus 9 it provides. So 18 plus 9, how much? 27 microcoulomb will be the answer. So C will be the option. Okay, quite interesting question, but it is very easy. Let's move on to our second question. So this is our second question. Find the time constant for the RC circuit. Okay, so this is very easy. Look, these are in parallel, so we'll add them, and these are in series, so we'll again add them. So R equivalent will be 3 ohm for the circuit 1, right? And C equivalent will be 4 plus 2, 6 microfarad. And time constant we know it is RC. So we'll just multiply them and we'll get 18, right? Microseconds. 18 microseconds will get. So A or B may be correct. So let's just find this. So look, these are in series. So for circuit 2, C equivalent will be 4 into 2 upon 4 plus 2. So it will be 8 upon 6. And R equivalent, again these are in parallel. So we'll write it as 2 into 1 upon 3. So it will be 2 by 3. So for this was for the first circuit. Now the time constant for second is RC. So it will be 2 by 3 into 8 by 6. So this will be 3 and we'll get 8 by 9 microsecond. So B option is correct, right? Okay, let's move on to our third question. So this is our third question. Now what we have, a 4 microfarad capacitor and a resistance, this are in series with a 12 volt. Okay, so this situation we have a capacitor of 4 microfarad and a resistance of 2.5 mega ohm. Okay, so this capital M represent mega ohm, 10 raised to power 6. And we have a battery of 12 volt. All are connected in series. Now find the time after which the potential difference across the capacitor is 3 times the potential difference across resistor. So let's say that the potential across this is x. So this will be 3x, right? And we know at any moment of time the potential difference across them, the sum of potential difference across them must be equal to 12. So you can write it as 3x plus x equals to 12. So we'll get 4x equals to 12. So we will get x equals to 3, right? Now we know the formula for potential, so how potential difference across this capacitor will change, right? How it will change? So it will be V is equals to, yes, it will be V naught into, right, 1 minus e to the power minus d by RC, right? Okay, so V naught is 12 and V becomes 9, right? So this 3x is 9. So it will be 9, 1 minus e to the power minus t by RC. So R and C will multiply. So RC will get 4 into 10 raised to the power minus 6 into 2.5 into 10 raised to the power 6. So it will be what, 10? So divided by 10. Yes, so we'll get 9 by 12 equals to 1 minus e to the power minus t by 10. So it will get cancelled. We'll divide them by 3. So this will 3 by 4. So we'll get E minus T by RC will be 1 minus 3 by 4. It will be 1 by 4. So let's take natural log both sides. So it will be minus T by RC equals to minus 2 ln2. Yes, ln4 to the power minus 1. So it will be minus 2 ln2. Negative will get cancelled and t will be 20 ln2. So 20 into 0.693. So it will be 6.93 into 2. So 13.86 seconds will be the answer. Okay. So A will be the answer. Right? Quite interesting. Let's move on to our fourth question. So these are simple questions. That is why I'm going with a bit of more speed. Okay. So this is our fourth question. Now we have a capacitor is charged using an external battery and the resistance X in series. Again, the dashed line showed the variation of ln I with respect to time. If the resistance is changed to 2x, the new graph will be. Okay. So we know how the current will vary. So current will vary as I naught e to the power minus t by RC. And I naught we know it is V naught by R. So let's put all those values here. It will be V naught by R e to the power minus t by RC. And if you take natural log both side, we'll get ln of V naught by R, right? Plus minus t by RC. Right? Okay, perfect. So look, so this is in the y-axis. This is our constant. But look, the resistance is changed to 2x. Okay, so just write it as ln V naught by R plus, and this is t. So it will be minus x by RC. Okay, now if you compare it, y equal to c plus mx. So m will come out to be minus 1 by RC, right? And this c will come out to be ln V naught by R. Okay? Now the dashed line showed, so this was the initial line. Now, as the resistance become double, so if this becomes 2 times, so slope will be, so look, the slope is already negative. So let's say the initial value of the slope is minus 10, and now the final value become minus 5. So how will you draw these graphs? So initially, let's say this was our line, right? Now the slope is tending to 0, right? So the graph must be like this. Okay, so look, S and Q will be the answer. Either S or either Q will be the answer. Okay, so P and R must be wrong, right? So from Q and S, which one should be? So look, this graph was here. So this was our initial CI constant, right? So this was our initial CI. Now, if R is increased, this whole value will decrease and hence ln will decrease. So C will decrease. Yes, are you getting? So C will decrease, then graph must be here. So it will be the Q. So B option will be there. Okay, quite interesting. Let's move on to our fifth question. Okay, let's start with our fifth question. So we have the circuit with steady current in it. The potential drop across capacitor must be. Okay, so look, what will be happening that in this wire current will be 0. So the current will be flowing in this wire. So let's say the current flowing like this, right? In this wire there will be no current, right? So let me cross that. So let's use the Kirchhoff's law here. Okay, so if you use Kirchhoff's law, we'll get this will be plus, so this will be plus 2 minus I into 2R, and this will be minus I into R, and this will be minus 1 equals to 0, right? So we will get minus 3IR equals to minus 1, right? 2 minus 1. So we'll get I as 1 by 3R. Okay, so it is V, so we'll just write 2V to V. This is V, so this will be V. So current will be V by 3R. Okay, now look, let's consider this point as zero potential, at zero potential. So this will be at zero and this will be at zero. Now this point must be at V potential. This point must be at a V potential, and okay, so we don't need it. And the current in this is zero, so this point must be at V potential. Right? So this is simple, right? We don't even need this. Oh, so if this is at V potential, so if this is at a zero and this is at V potential, right? Okay. Uh, so this should not be okay. Look, there will be a potential difference here. So this must not be at V. So it must be at V dash. Okay, so this is wrong. Right. So okay, so yes, we need to find this current. Actually, we need to find this current. Now what happens here is, so let me rub this. Okay. Now we need to find the potential difference here. So look, the if this is at a zero potential, so this wire and this wire, right? So we'll write it as this wire is on one, this wire is at two. So wire one and two are in parallel. So the potential difference across them will be constant. Okay. So look, if this is at a potential zero, this must be at potential V and this must be at potential V1. So we need to find V1 minus V and V1 minus V, right? So we need to find V1 minus V. Okay. So this we required. So this is required. Now we know from this wire is at a potential V1, V1 minus 0. And this wire must be at the same potential. So let's find the potential difference across two. So potential difference across wire 2. Let's find the potential difference across wire 2. So it will be, let's start with this. So it will be plus 2, right? So this is at V1, so this must be at V1. So plus 2 minus I into 2R, and this will be equals to V1. Okay, so we'll get V1 as 2 minus I was, so 2V minus V by 3R into 2. R will get cancelled, so we'll get 2. This is 6 minus 2, so it will be 4V by 3. So V1 is 4V by 3, and we'll put it here, so it will be 4V by 3 minus V. So we'll get V by 3. Okay, so this is our answer. Okay, let me walk through this question again. Look, the current in this wire is 0, right? Current in this wire is 0. So we'll just find the current in this section. Now, to find the potential difference across C, we must understand that we'll consider this point as 0 volt. Okay, so this point is at V volt, and we'll consider this as a V1 volt. Now we need to find V1 minus V. So we need to find V1 minus V. Now what will be happening is, look, this first wire and this second wire, they are in parallel. So potential difference across these two wires must be same, right? So I have found the potential difference across this. So V1 minus 0 is how much? It will be 4V by 3. So I'll simply get V1. So if I get V1, then V1 minus V will be the answer. So it will be 4V by 3 minus V. So C is the answer. Okay, quite easy question, but there can be a bit of confusion. So be careful. Yes, let's move on to our sixth question. So this is our sixth question. Perfect. We have a parallel combination of, so this is a parallel combination of capacitor and a resistor, right? Okay, perfect. So this is 0.1. No, so this is 10 millifarad, and this is 0.1 mega, and this battery is of 1.5 volt. the time required for capacitor to get charged up. So look, they are in parallel, so potential difference across them must be same. So within second, I mean within instant, this will get charged. So time required will be zero. Okay, so time required will be zero. Within instant, it will get charged, right? As soon as you let's say this is a switch. As soon as you close the switch, the potential across this capacitor will become instantly 1.5 volt. And as it will become 1.5 volt, that means this capacitor must have some charges, right? So within instant, as soon as you close the switch, this capacitor will get charged. Okay, so let's move. This was our sixth question. Let's move on to our seventh question. Okay, perfect. So this is our seventh question. Now we have a circuit. Each resistance are of 1 ohm, labeled like this. Two ideal batteries with voltages E1 and E2. Which of the following statement is correct? So let me add the statement also. Okay, perfect. So yes, so these are the statement which we require to solve. So we need to find the current in R1, R2, R3 and R5. So 1, 3, 2, where is 2? This is 2. So 1, 3 and this. Okay, so let's find how should we solve this. Look, about this line, it is symmetric. So we can use folding symmetry. So let's fold it here. So we'll get this, our cell. This is a resistance. This is our cell and this is our resistance, right? Now look, this is one, this is one, and these are in parallel. So we'll just make it 1 by 2. Okay, now this will also become 1 by 2. This will stay same. It will be 1 1, and again this resistance will become 1 by 2, right? Now we can use Kirchhoff's law. So I'll use uh, in R1 we'll say the current is I1. Okay, current is I1. So in this it will also be I1, right? And in R3 we'll say the current is I3. So we'll just write it as I3. So this is I3. Okay, so in this I1 and in this I3, so in this it will be, let's say, I1 minus I3. Okay, so in this it will be I1 minus I3. This is at 12 volt and this is at 6 volt. Now let's use the Kirchhoff's law here. So in this loop, let's start. So it will be minus I3 into 1 plus 6 minus I3 by 2, and in this it will be plus I1 minus I3 by 2 is equals to 0. Okay, let's solve. So this is I1 by 2 minus 1 1 and this is 2. So it will be 2I3 plus 6 equals to 0. So we'll just write it as I1 minus 4I3 plus 12 equals to 0, right? So this is our first equation. This was our first loop. This was our second loop. So this was loop 1. Okay, now let's go to loop 2. Again, we'll go clockwise. So from here we start. So this will be minus I1 into 1 plus 12. This will be minus I1 minus I3 by 2, and this will be again minus I1 by 2 is equals to 0. Okay, now here this is I1 and this will be 2I1, so minus 2I1. Okay, and this will be plus I3 by 2 plus 12 is equals to 0. So we'll have minus 4I1 plus I3 plus 24 is equals to 0. Okay, so we have these two equations. So let's solve, and let me multiply this equation by 4. So we'll just write it as 4i1 minus 16i3 plus 48 equals to 0. And let's add them. So we'll get this will be minus 15i3 plus this will be 72, right? Equals to 0. So i3 will be 72 by 15. So we can divide it with 3. So this will be 5 and this will be 24. So we'll have 24 by 5, right? So how much it will be? It will be 4.8 ampere. So this is I3. Let's put I3 in this equation. So we'll get I1 minus, uh, so it will be 4 into 24 by 5, right? Plus 12 is equals to 0. So we will get I1 as, this will be how much? So this will be, let me use a calculator really fast. So 19.2 minus 12. So this will be 19.2 minus 12. So I1 will be 7.2 ampere. Okay. Now let's solve. So look, uh, how much I3 was 4.8. So this is 4.8. Okay. Let me write it with front one. And I1 is 7.2. Okay. Perfect. Now look, in R1 and R3 current will be same. But in R6 or let's say R5, so we have clubbed them together, means they become uh, in parallel, right? So if I say, let's say it has I2 current and this also has I2 current, means when I club them together, it becomes 2I2. So in this, it is I3. So I3 is actually 2I2. Are you getting me? Yes, because when you connect two resistance having equal current in parallel, then the total current will become twice. Okay. So if this they have I2 and I2 current and I club them together, then means I3 must be twice of I2. Okay, are you getting me? So let's find. So in R1 it is 7.2. So yes, A option is correct. In R2, so in R2 in this wire current must be double, right? So in this wire, let's say the current is I4. Okay, so I4 must be equals to I1 minus I3 by 2. Yes, so I1 was 7.2 minus I3 was 4.8 divided by 2. So how much it will be? So it will be uh, 2.4 divided by 2. So it will be 1.2 ampere, right? So I4 in this wire it is 1.2. B option is correct. Now in R3, so in R3 it will be 4.8. So C option is also correct. Now the magnitude of current flowing through R5, R5. So this was R5. So it is I2. I2 is how much? So I2 is I3 by 2. So I3 was 4.8. So it will be 4.8 divided by 2. So it will be 2.4. So this is also. So all options are correct. Okay. Quite interesting question it was. Seventh. Let's move on to question number 8. Right. So we have a long wire carrying current I, which is 2 ampere. Okay. And semicircular conducting rod is placed beside it like this. Both rails, these are two rails, are parallel. Two ends of semicircular are at a distance 1 centimeter and 4 centimeter. Okay. At the time t equal to 0, the rod starts moving on a rail with speed v. Okay. The resistance, this R is 1.4 and this is 5 microfarad. farad. Okay, they're in series. T equal to 0, C naught is uncharged, which is the current. So maximum current and maximum charge on the capacitor and the maximum current in the resistor we need to find. So look, due to this current, there will be magnetic field in this direction. And due to this magnetic field, and look, this rod is moving like this. So area between them is changing. So there will be an EMF. Okay, there will be an EMF. So how should we solve this? How should we solve this? So we'll simply use the formula. So EMF is minus d phi by dt, right? So EMF will be minus d phi by dt. Okay. Now the problem with this question is like, look, this is infinite wire, and we know magnetic field due to infinite wire will be mu naught I upon 2 pi x. Okay. So we need to take an integrating element over here. Then only we can find the potential difference. So look, this is our y carrying current I, and at a distance x we can take integrating element dx, right? We can take integrating element dx. On this, magnetic field will be mu naught I upon 2 pi x. Okay, are you getting? Perfect. Now let's say the integrating element has a length L, right? So this is the length, okay, and this is breadth. So it's, let's say it is B. Now look, so we'll put those values here. So EMF developed will be minus d by dt. Magnetic field, it will be mu naught I upon 2 pi x, right, into area. So area will be B into dx. Okay. Now look, current is not changing with respect to time, and x and dx is not changing. So we'll just put them outside. So it will be mu naught I upon 2 pi x dx. Okay. And so look, this EMF is very small. So this is dE. So it is a very small EMF. Okay, because integrating element is very small, so we are considering in this, and it will be dB by dt, right? So dB by dt is changing with V, so we'll just put it as V. So it will be mu naught I V upon 2 pi x dx. So this is the small EMF which is developed across this integrating element. Okay, right? And we are considering about the whole area, so we'll just integrate them. So we'll get mu naught I V upon 2 pi ln x, and the limit will be putting it from 1 to 4. So it will be 1 to 4. So this is the net EMF which is developed across the this loop, right? So how much it will be? So EMF will be mu naught upon 2 pi. So it will be 2 into 10 raised to power minus 7. If you multiply it by 2 and divide it by 2, so it will be mu naught upon 4 pi, and 2 will be this. Current I is 2. V, speed of this rail is 3 meter per second. It is moving with the speed 3 meter per second, right? Ln 4 by 1. So we'll get, this will be 4 and this will be 12 into L 2 ln 2 into 10 raised to power minus 7. This is the EMF. So EMF will be 24 into 0.693 into 10 raised to power minus 7 volts, right? Okay. So how much it will be? It will be 24 into, let me use a calculator really fast. So this will be 16.632 into 10 raised to power minus 7 volts. Right? So this is the maximum EMF which is going to produce across this loop. Okay. So this question becomes simple. We have a resistance, we have a capacitor, and we have a potential difference of 16.632 into 10 raised to power minus 7. The resistance is 1.4 ohm and the capacitance is 5 microfarad. So the maximum current I naught will be V naught by R. So it will be 16.632 divided by 1.4 into 10 raised to power minus 7. Okay. So if I use my calculator really fast again, divided by 1.4, right? So it will be 11.88 into 10 raised to power minus 7 ampere, right? So none of the options are matching. Let's find the maximum charge on the capacitor. So I'm writing it here. So Q will be equals to CV naught, right? So this will be the maximum charge. So C is how much? It will be 5 microfarad, and it is multiplied by the potential. It will be 16.632 into 10 raised to the power minus 7. So 16.632 into 5. So you'll get 83.16 into 10 raised to the power minus 13. So we can write it as 8.3 into 10 raised to the power minus 12 microcoulomb. Oh, so it will be coulomb, right? So C option is correct. Okay, so B is wrong, of course. So we get C answer. Okay, let's move on to question number 9th. Let's move on to question number 9th. Right. So we have the situation circuit shown initially. There is no charge. S1 and S2 are open. Values of these are given. This statement is correct. Okay. So key S1 is kept closed for a long time. S1 is kept closed for a long time such that capacitors are fully charged. Now the key S2 is closed at a time. Instantaneous current across 30 ohm will be 0.2. So we'll choose which option we can solve it like the fastest. Okay. So if the key S1 is kept closed for long time so that capacitor are fully charged, the voltage across C1 will be 4 volt. Okay, so let's solve this one. So if S1 is closed for long time, we'll have the situation like this. So this will be a capacitor. This is our cell. This is our resistance. We have a capacitor. Again, we have a resistance. So we have this, and we have again a capacitor. And let's change these, right? So this is a 5 volt C4. So this is C4. It is 80 microfarad, right? So C4 is 80, C1 is 10, right? So C1 is 10 microfarad, and this is C3. So C3 is again 80. Okay. Now, if it is kept for close time, there will be no current. So I will be 0 in the circuit. So we need to find the potential across C1, right? So potential across C1. So look, this 80 and 80 are in series, so we can write C equivalent for that. So the circuit will be like this. So this is our capacitor, and we can remove those resistance because there is no current. And this is C equivalent. So if they are in series, C equivalent will be 40, right? So this is an easy way to solve it, right? So this is 5 volt and this is 10 microfarad. And we know V is inversely proportional to C. So let's say potential across this is V1. So V1 will be this C equivalent upon C1 plus C equivalent into V. So C equivalent is 40 upon 40 plus 10. So it will be 50 into V is 5. So this will get cancelled, 5 will get cancelled. So we'll have 4. So B is the correct option, right? Let's move on to, let's check C. At time t equal to 0, S1 is closed. The instantaneous current in the closed circuit will be. So this is quite easy. Again, let's solve this. So as soon you close this, we don't need capacitors actually, right? So we have only two resistance. This is 70 ohm and this is 100 ohm. Okay, so we have the third one, 30 ohm over here. So the R equivalent, they are in series, so it will be just sum of them. So it will be 20 ohm and V is 5 volt. So instantaneous current just after it is closed, it will be 5 upon 200. So it will be 25 milliampere, right? So C is also correct. Let's check D option now. As one is kept closed for a long time, such that capacitor are fully charged, the voltage difference between P and Q will be 10 volt. So look, voltage difference between P and Q will be same as potential difference across these 2 points. Let's call them RS. And we know after a long time the current will be zero in this. So the potential drop across RS will be same as potential drop across C1 and it will be same as PQ. So we know potential difference across C1 was 4 volt. So potential drop across RS will be 4 volt. So potential drop across PQ must be 4 volt. So this D option is absolutely wrong, right? Now let's move on to A. Now let's move on to A. Saying after S1 is kept for a long time such that capacitor are fully charged. Okay. Now S2 is closed. Okay, so let me make the diagram. S2 is closed. Now S2 is closed, so the diagram will be like this. This is our capacitor. This is closed. We have another capacitor, resistance, cell. We have capacitor C1. We have a resistance 70 ohm, and then we'll join them. We have 100 ohm. Now here we have 5 volt. This is 30 ohm. This is capacitor C3. This was C1. This was C2. And this is C4. Okay, and we'll join them. Now, as S1 was closed for a long time, the potential across this was 4 volt, right? So this was positive, this was negative. Now, if it was 4 volt, the potential across these must be same. So it is 30 minus 4 is so 5 minus 4 is 1. So across them it will be 0.5 volt, and across this capacitor it will be 0.5 volt. Just before S2 is closed. Okay, the situation was like this. Now the S2 is closed. What happens? So look, we know the potential across this. So it is 4 volt. So let's call it 4, right? Let's call it 4. So this will be 0. Okay, and we have this is 10 volt. So this point is at 10. Okay, now look, the situation is we know the potential difference across this, and as soon as you close it, so we can use the equation here, right? So let's use the equation. Let's use the equation for a moment. Let's use, so it will be 4, and at instant there will be no charge here, so it will be 0. And let's say the current is like this, I, so it will be minus 10I, right? And this will be minus 10, right? Okay, is equals to 0. So how much it will be? So it will be, yes, so this was at 4. So the potential difference across this was 4, right? Okay, so this will be 10I equals to minus 6. So I will be minus 0.6. Yes, are you getting? Is it correct? So this was 4, this is 0. In this capacitor, there is, okay, so this is 30 ohm. I have written it 10. So this is 30. Yes, so answer will be 0.2. Minus shows the direction I have took it in the wrong way, right? So 0.2. So this A must be correct, but no, A is not correct, right? So A is not correct. Why? Look, the problem is as soon as you connect this, these capacitors starts to push charge here. Okay. So due to this, the current will not be same as 0.2. It will be different. So we can't use this method because as soon as you close it, the potential difference will not remain 4, it will be different. Okay, so this method is not correct. So let's solve this. Okay, so look, as soon as you close it, the potential will not change across these, right? So it will be the same. So let's write that current in this is I, okay, and current in this is, let's say, I1. Okay, so in this it will be I plus I1. Now we'll use the Kirchhoff's law. Okay, so let's use Kirchhoff's law in loop 1 in uh, anti-clockwise. Let's go anti-clockwise. So it will be -4, potential drop -4, and the resistance of this resistance is 70, right? So this is 70. Okay, so right now we'll use minus I plus I1 into 70, and this will be plus 10. The current is like this, it will be minus 30I equals to 0. Okay, so we'll get minus 70 I1, and this is minus 70 minus 30 minus 100I, and this will be plus 6 equals to 0, right? Let's use Kirchhoff's law in this loop now. Okay, or we can use in this bigger loop. Which one will be easy? So here there are a lot of things, right? Okay, now you will say, sir, what is the potential difference here? So it will be 0, because as soon as you close it, there was no charge on it. So there will be no potential difference here. Okay, so as soon as you close it, there will be no potential difference here. So let's use in loop 2 now. Leave it. So loop 2. Okay, let's go with the loop 2 in the anti-clockwise. Let's start from here. So 0, this will be plus plus I into 30 minus 10. In this, the current is I1 in this, right? So it is I1 in this one. So it will be minus 100 I1, and here it is connected with negative, so here it is negative, here it will be positive, so we'll write it as minus 0.5. Now here it will be minus 30 I1, this will be plus 5, and here this will be plus, this will be minus, right? So here it will be minus 0.5 equals to 0, right? So this is I, and this is I1, I1. So we'll write 30I minus 130 I1. Okay, this is 5. This is minus 10, so minus 5 minus 6 is equals to 0. Okay, perfect. So how will you solve it? Uh, so this is 100, this is 30I. So we'll just multiply it by 10 by 3. Okay, so we'll get 100I minus 1300 upon 3I1, and this will be minus 20 equals to 0, and this will write it here minus 100I. So this is our second equation, right? I have modified second equation here, and this is our first equation. So I'm writing the first equation again. Okay, so it was minus 100I minus 70I1 plus 6 equals to 0. This will get cancelled, and we'll have 1300 plus 210. So it will be 1510 divided by 3 I1 minus, and this will be minus 14 equals to 0. So I1 will be minus 14 into 3. It will be 7. It will be 42, right? Divided by 1510, right? So negative shows that direction I have took it in the opposite way, right? So let's calculate. So 42 divided by 1510. So it will be 0.278 something ampere. Okay. Now, but we need I, right? So we need I. So if you put this value I1 in an equation, let's put it in here. So it will be zero point 0, right? So 0.0278. So let's put this value in equation 1. So it will be minus 17 to minus 0.0278 minus 100i plus 6 equals to 0. So you get, let me use the calculator really fast. It will be 17 to 0.0278. It will be plus 2 almost minus 100i plus 6 equals to 0. So we get 100i equals to 8. So I will be 0.08 ampere. Okay, now this is the problem. That is what I'm saying. So in this, current will not be 0.02. So it will be 0.08, right? So actually A option is wrong, right? So this is extremely good question. So it's nice. Huh? So be careful while solving these type of questions. Okay. So this was our ninth question. Let's move on to our 10th question. Right. So we have a circuit like this. Connected current in the resistance R2 is 0. So if it is 0, let's consider this potential as 0. So this must also be 0. Now if this is 0, this must be V2. So this point is at V1. Okay, so this must be at V1. Now if this is 0, this must be at V2 and this must be 0. Now if the current is 0 in this, so current will be like this in these wires. Okay, so current will be in the outer, like this periphery of the circuit, right? Okay, so look, the current is same in both the resistance, so we can write it as I1 equals to I3. Current in 1 is equals to current in 3. So I1 will be V1 by R1, and in I3 it will be V2 by R3. Okay, so this condition must be followed. So V1 by V2, V1 is equals to V2, then R1 must be equal to R3. This is correct. V1 is V2. Then R2, R2 can be anything, but R1 and R3 must be same. So B is also correct. Okay. Let's check C option. So V1 is equals to 2V2. So if you put 2V2 here, so we will get R1 equal to 2R3. So R1 equal to 2R3. So this is wrong. Now let's put 2V1 as V2. So V2 will be 2V1. So V1 upon R1 equal to 2V1 upon R3. So we will get cancelled. So R3 will be 2R1. So R3 will be 2R1. So the D is correct. Okay, it's quite easy question again. Let's move on to next 11th question. So this is our 11th question. Let me zoom in a bit. Right. So we have at t equal to 0, the terminal A in the circuit is shown. The figure is connected to P. Okay. An alternating voltage this with I naught 1 ampere and omega is this. At t equals to 7 pi by 6 omega. The switch from B to T, it is moved from B to D. So I mean this alternating supply is disconnected. Now the total charge Q flows through the battery to charge the capacitor fully. These are given. Okay, so when B and A was connected, this capacitor must be charged, right? So the situation is like this. Now current is in this direction. Okay, so from B to A, we'll consider this B and this is A. Okay, from B to A, it is moving like this. The direction is given, right? So initial direction we must know from where it is going. So it is going in the clockwise direction like this. So it will be I naught cos omega t. Now we need to know the charge. So we know I is dq by dt is equals to I naught cos omega t. So dq will be I naught cos omega t dt, and we'll integrate them, right? So initially there was no charge, finally it is q. Initially time is 0 and the final time is 7 pi by 6 omega. So we'll get q as I naught. This will be sine omega t divided by omega from 0 to 7 pi by 6 omega, right? 7 pi by 6 omega. Now q will be I naught upon omega sine 7 pi by 6, you can write pi plus pi by 6. So this will be I naught minus omega sine pi by 6, which is 1 by 2, right? So minus sign indicate that this plate will be minus q charge and this will be plus q. So this plate up will be minus q and this will be plus q. Okay, how much it will be? I naught. Let's find I naught first. So I naught was 1 and omega was, so I naught was 1. It is given, right? We don't need to find it. This is 500 divided by 2. So it will be minus 10 raised to power minus 3 coulomb. Okay, quite interesting. So let's check the option first and then we'll calculate further points of further options. Magnitude of maximum charge on the capacitor before this time is this. Look, and you look, we get 10 is 1 minus 3 and you will mark this as correct. This is wrong. Before this, there will be a situation where the charge was maximum and it is not this. So the maximum charge Q max will be I naught by omega sine omega t from 0 to pi by 2 omega. At this time, the charge will be maximum. So it will be I naught by omega, right? This is I naught by 2 omega. So it will be 2 into 10 raised to the power minus 3 coulomb. So this A option is absolutely wrong. Okay. At this time, definitely charge is this. But what will be happening is that before this time, 7 pi by 6 omega, there was a time where the charge becomes 2 into 10 raised to power minus 3. Then charge starts to decrease, then the opposite start to accumulate. It was like that. So this is absolutely wrong. Now, the current in the left part of the circuit just before this is clockwise. Is it clockwise or it is anti-clockwise? So current will be in anti-clockwise, right? Initially it was at clockwise, then after some time, after like time pi by omega, the current switches its direction and it becomes anti-clockwise. So B option is also wrong. Are you getting it? It's quite interesting question. Let's move on to C. Immediately after A is connected to D, the current in R is 10 ampere. So let me make the situation now. Immediately after A is connected, situation is like this. We have a capacitor, we have a resistance, we have a battery of voltage this. Like the situation is like this. Now the charge here is minus Q, here is plus Q. This is 50 volt and this is 10. Now, if I know capacitance, it is 20 microfarad. Let's find the potential difference. So V will be Q by C. So Q is 10 raised to power minus 3 divided by C, 20, right? So it will be simply how much? So it will be in the microfarad it was. So let me write it like 10 raised to power 6. So it will be 1000 upon 20. So this will be 50 volt. So this is negative. So the potential across here is 50. Now, just after it is connected, let's use the Kirchhoff's law. So from here I'm starting. Look, this is at high potential, so it will be plus 50 minus I into 10 and plus 50 is equals to 0, right? Okay. Now, so 10I will be 100 and I will be 10 ampere. So yes, C is correct. C is correct, right? Now let's check the option. So Q is 2 into 10 raised to power minus 3. Q is the total charge. Q, what is Q? So a total charge Q flows from battery to charge the capacitor fully. Okay, so we are talking about a long time. So after a long time, what happens is this start to give charge Q to this, right? So this will become 0, then this will become negative, and eventually what will happen? This will become plus Q, this will become minus Q, right? And all the potential which was 50 volt, it will become 50 volt here. Look here, this was at a less potential, this was at high potential. Now it will become like this. So this will become at high, this will become at high potential, and this will at low potential, right? So how much charge will be accumulated, right? So it will be 2Q, right? And Q was 10 raised to power minus 3, so it will be 2 into 10 raised to power minus 3. Yes. So this was Q, right? And now the charge will become 2 into 10 raised to power minus 3. So look, the charge is Q, but battery provides a plus this capital Q charge, which is 2Q. Okay. So D will be the correct option. So C and D are the answers. Let's move on to our 12th question. So this was quite interesting, right? Let's move on to our 12th question. So we have capacitor C1 and C2 are separately charged by common battery. Okay, let's call this battery as B. So this is C1, 1 microfarad, and we have another capacitor C2. This is 2 microfarad. Both are charged with V potential. The two capacitors are then separated and allowed to discharge through equal resistor. So now these capacitors are connected with the resistance. Okay. Now what will be happening here is the potential is same V, both have same potential, but here it will be Q1 and here it will be Q2 charge. Okay. And resistance is also same. The current in each of the two discharging circuit is 0 at t equal to 0. So n t equal to 0, current will be maximum. Okay, and it will be, so how will current will change here? So it will be I naught t to the power minus t by RC. Okay, so it will be maximum. So A is definitely wrong. Okay, the current in two discharging circuits are equal but not 0. So this is correct. Why it is equal? Because I naught, let's find I naught. I naught will be V by R, V naught by R, and both are charged with V potential, right? So B is correct. So current will be same in both. The current in two discharging at t equal to 0 are unequal. So this is wrong. Now capacitor C1 loses 50% of its initial charge sooner. Then C2 loses 50% of charge, right? So let's find the time constant for them. So time constant is, so for this, let's call this 1, this call 2. So T1 will be R C1. So it will be R into 1. So that is R microseconds, right? So this is T1. Now let's find time constant for 2. It will be RC2. So it will be 2R microseconds, right? So what is saying that C1 will take R seconds, R microseconds to become, so it will be R upon ln2, right? You know that, right? So you know T half, time taken to lose half the charge, it will be ln2 divided by time constant, so it will become RC. Yes, you must know this formula. So look, the capacitor of 1 took the time 0.693 into R, whereas the half-life of, you can say, the time where 50% of charge is lost for 2 will be 0.693 into 2 hours. So C2 is taking more time, compared to C1. So C1 lost its charge earlier than C2. So D option is also correct. Okay, quite interesting question. Let's move on to 13th question. Okay, so we have two questions here, 13th and 14th. So we have given this circuit, switch S is connected to P. Okay, long time no, so that charge on capacitor becomes Q1. Okay, so circuit will be like this. So this is our battery. This is resistance 1. This is resistance 2. This is our second battery. And we have a capacitor like this and like this. This is 2 volt. This is 2 ohm, 1 ohm, and 1 volt. Now, after a long time, what happens? I in this is 0. So simply current will be like this in I, right? So I need to find the Q1 charge first, right? So Q1 and Q2 they are asking. So first we need to find the Q1. So look, the potential difference across this will be same as potential difference. So let's call this potential V. Let's call this potential 0. Okay. So this is 2 and this is 1. This is 0. So 0 volt, 2 volt. This is V. Okay. And this is 0. So let's first find the current in this. Okay. So current will be how much? So it will be, let's use the Kirchhoff's law in the clockwise. So it will be plus 1 plus minus I minus 2I, and this will be minus 2 equals to 0, right? So we'll get minus 3I equals to 1. So I will be minus 1 by 3. So it's in the direction is wrong. So no worries, direction will be like this. Now let's find V. If we get V, we'll get the potential difference across this capacitor, and hence we can find the charge. So here we can use it. So it will be V minus 2 will be equals to I into R. So it will be, right? So potential difference is how much? It is V minus 2. And the current is, so the current is in opposite direction, right? So current is in this direction. Okay. So current in this direction, that means this must be at high potential. Okay. So this must be at high potential. We can write 2 minus V is equals to 1 by 3 into 2. So we get V as 2 minus 2 by 3, which is 4 by 3. So we get V as 4 by 3. Okay. So Q will be C into V. So it will be 4 by 3 into 1. So it will be 4 by 3 microcoulomb. So the first answer will be 4 by 3. It is 1.33 microcoulombs. Okay. Let's solve for Q2. So now switch to position Q. Okay, so initially it was at P, now it is switched to Q. After a long time, charge on the capacitor. So this is quite this situation is quite simple, right? So now situation is like this. Now this has some V potential, which is 4 by 3. We have calculated, right? But it does not matter. Eventually, this battery will provide the charge, new charge to it. So we'll just consider it as Q2. Okay. Now after a long time, the current will be like this in this circuit. So it is I, let's say it is I. So this is 1 ohm, this is 2 ohm. Now the current will be simply, so this is in series. So this is 3, this is 2. So 2 by 3 ampere, right? Now let's consider this point as 0. So this will be 0. So this is at 2, and let's say this is at V. So 2 will be more because in the direction of current potential drops. So you will get V minus, so 2 minus V is equals to IR. So I 2 by 3 and R is, so how much it will be? So V will be 2 minus 4 by 3. So V will be 2 by 3. Now if V is 2 by 3, then Q2 will be 2 by 3 into 1 microfarad. So it will be microcoulomb, right? So 2 by 3 microcoulomb. So it will be 0.67 micro, right? Quite simple question it is. Let's move on to our last question. So this is our 15th question. Let me put the other half there. Okay, perfect. So let's zoom in a little bit. Okay, perfect. Oh, so there are two switches again. Let's start. So we have three identical capacitors, C1, C2, and C3, 1 microfarad each. They are uncharged initially, so they're connected like this, filled with the material. So this is filled with the material. So now C1 becomes ER microfarad. Okay. Mm, this is 8 volt. Okay. First, S1 is closed. So S1 is closed while the S2 switched is kept open. So when it is done like this, so the situation will be like this. So this is C3, this is 8 volt. So potential across becomes is 8 volt, right? Okay. So when C3 is fully charged, S1 is opened and S2 is closed. Now the situation is like this. So this is C1, this is C2, and we have a capacitor like this. So this is C3, this is C2, and this is C1, and this is filled with the material, right? And the potential across this becomes 8 volt. So here it will be plus Q, and here it will be minus Q, and the potential becomes 8 volt. Okay, let's find the Q also. So Q will be 8 into 1, so it will be 8 microcoulomb. So here the charge is 8 microcoulomb. Here it will be minus Q, right? Now when all capacitor reach equilibrium, the charge on C3 is found to be 5 microcoulomb. Okay, so initially it was 8. Now what will happen? 3 microcoulomb of charge must have transferred to these plates. So here it will be plus 3, here it will be minus 3, here it will be plus 3, here it will be minus 3 coulomb, microcoulomb, right? Now the potential across these must be same. So let's consider the potential across this is V, and let's say it is 0. So if it is 0, let's say it is V1. Okay, so V must be equals to V1, right? So let's first find V. So it will be the new charge is how much? 5 microcoulomb, right? So V will be, so first find for this potential for this. So it will be Q upon C. So 5 upon 1. Yes, so across this, the potential is 5 across 1. Now across this, potential must be sum of these two. So it will be, let's say this is V2 and this V3. So this will be V2 plus V3. Now V2 is how much? So it will be 3 upon capacitance ER. And V3 is how much? So it will be 3 upon 1. Okay. So 5 will get 3 upon ER plus 3. So I'll get 3 upon ER is equals to 2. So we'll get ER as 3 by 2, which is 1.5. So answer will be 1.5. Okay. So this question is quite interesting again, but nothing to worry. It's a very simple question. So these were our 15th question. Let's finish the video today. Thank you so much.